Welcome to the fifth module, this third week. This entire week we had been looking at the forced oscillator. So, we will do some problems today, some selected problems. Let me straight away get into the first problem. So, in this case a block of mass 2 kilogram is hung from a spring. So, the situation can be picturized like this. So, I have a spring like this, and what is done is to this spring a block with mass 2 kg is attached to it. So, when you do that, the spring will extend, and the problem states that it stretches by 2.5 centimeters. So, this is a block of 2 kilograms, and so the stretching is by an amount 2.5 centimeters. And we are also told that the top end of the spring, which is this part here, which I am marking now in red, is also undergoing harmonic oscillation, and it has an amplitude of 2 millimeter. So, this will be 2 millimeter. So, it goes up and down 2 millimeters on either side from the equilibrium position. And we are also given that the Q value of this system is 15. So, the first question is find what is omega 0. Omega 0 is the natural frequency. So, we would like to know what is the natural frequency of the system. So, this can be done from the information which is given in the first part of the problem. So, we are told that you have a spring and you add the mass, the spring stretches by about 2.5 centimeters. Then the stretching, which is let us say x, would be given by the following. So, the weight, which is mg, is equal to k times x. From this equation we can find omega 0 simply because k by m, which is equal to omega 0 square, that would be equal to g divided by x, and g is let us say 9.81 meters per second square, divided by x, which is the amount by which it stretches, which is 2.5 centimeters. So, that would be 2.5 into 10 power minus 2 meters. So, we need to take the square root, that would give us a value for omega 0. So, approximately this value would be about 400 hertz, or actually I should take square root of this. So, omega 0 would be about square root of 400. So, approximate value is about 20 hertz. So, that answers the first part of the problem. The second part is what is the amplitude of the forced oscillations at this frequency, which is 20 hertz. What we know from everything that we studied is the amplitude of forced oscillations is f 0 by omega into mod z, which is the impedance. So, that would be f 0 by omega into square root of gamma square plus m omega minus s by omega whole square. Now, we need to evaluate this at omega 0, which is not too difficult. So, at omega equal to omega 0, the amplitude would be f 0 divided by omega 0 into square root of gamma square plus m omega 0 minus k by omega 0 whole square. So, in fact, the S stiffness constant here is just the spring constant k. So, remember that this S that I wrote down here should actually be k, which is the spring constant. So, here mass is already given. So, I know the value of mass. Spring constant is something that we know. Actually, we know the value of k by m itself. So, in fact, everything else is known except two things. One is we do not know what is f 0 and we do not know what is gamma. Gamma is easy to calculate simply because we know the value of q factor, which is given as q equal to 15. So, q which is equal to m omega 0 by gamma. So, you can see that we have calculated omega 0 already, m is already known and gamma is the only unknown here. So, gamma will be equal to m omega 0 by q. So, that would mean that mass is 2 kg. So, that is 2 multiplied by omega 0 is 20, that is 20 divided by q, which is 15. So, this will be 4 by 3, 4 into 2. So, it is about 8 by 3. So, I know gamma now, I know m, omega 0 is known, k is known. What about f 0? F 0 is the amplitude of the forcing, and the forcing here is such that you could see that the top of the pendulum oscillates up and down and the amplitude is 2 millimeters. So, that is our f 0. So, f 0 is 2 millimeters, which would be 2 into 10 power minus 3 meters. Now, we have everything that we need. So, we just need to plug in all these values into this expression for amplitude, which I will call it A. We know f 0, we know gamma. Let me also for completeness write omega 0 that we just calculated, which is 20 hertz. So, with all this information, you should be able to calculate the amplitude, and I will leave it as an exercise for you to put in the numbers and calculate the amplitude. So, that completes the first problem that we started with. So, this problem is based on the figure which is given here. What is shown is mean input power as a function of omega, which is the frequency of the driving. And we are told that this is for the case of a spring which is also damped, a mass hanging from a spring and it is damped. And we can assume that q value is sufficiently large, and the question is find the q value itself. And there is a second part to this question, which is that if you remove the driving part, the energy of course will start damping, and we are given how the energy is damping. So, the question is find the value of beta that appears in this equation. So, let us begin with the first part of the problem to find the value of q, and this is among the easiest of problems, because if you remember what we did in the earlier module, q value is simply omega 0 by omega 2 minus omega 1. So, omega 0 here is, we are not given a number, it is just omega 0. So, that is this quantity here. So, we do not know its numerical value, but it does not matter, but it is omega 0. But we know what is omega 2 and omega 0, omega 1. So, this is omega 1 and this is omega 2. So, all I need to do is to simply substitute those values. Omega 0 divided by omega 2 is 1.05 omega 0 minus 0.95 omega 0. So, this would be omega 0 by, I can take omega 0 common here, that will be 1.05 minus 0.95. So, omega 0 and omega 0 cancels. So, you can see that we do not need to know the value of omega 0 in this case. So, the answer is 1 divided by 1. So, the q value is 1. So, that is the result. So, the q value in this case is 1. Now, there is a second part to this problem. The driving force is removed, and as you would expect, if the driving is removed, the oscillator is going to start damping, and the energy damping is given here, that E as a function of time goes as E 0 times e power minus beta into t. So, if you go back to what we studied for the damped oscillator, you will realize that what is given as beta here, when you relate it to actually the parameters of the problem, that would be gamma by m itself. Q is m omega 0 by gamma, and this can be written as q by omega 0 is equal to m by gamma, in which case this is simply beta itself, and we know that q is equal to 1. Therefore, the value of beta in terms of omega 0 would be 1 divided by omega 0. So, that would be the result. Unless the value of omega 0 is given, we will not be able to obtain a numerical value for beta. So, it is written in terms of the natural frequency of the system. Let us start with the third problem. So, in this case, the amplitude of the damped oscillator at t equal to 0 is given as A, and it decreases to 1 by E of its value after n time periods. And if t 0 is the time period without damping and t d represents the time period with damping. Now, we need to show that in such a situation the ratio t 0 by t d is given by this. So, let us use the first statement of the problem, which is that A by A 0. So, A 0 is the initial amplitude, and A is amplitude at some time, let us say t. A by A 0 is of course e power minus gamma by 2 m into t. This is nothing new, this is something that we studied for the case of damped oscillator. Now, when when after n complete periods, the amplitude A simply falls to 1 by E of its value, which means that let us say that at t it is n times t 0. At this time, this is n times the period without damping. At this time, what we have is that gamma by 2 m multiplied by t, which is equal to gamma by 2 m multiplied by n into t 0, this is equal to 1. Only then the amplitude can fall by 1 by E of its original value. So, we have now a relation that connects gamma, m, n and t 0. So, all I need to do is take the ratio t 0 by t d, t 0 divided by t d, which will be equal to so t 0 is, remember t 0 is 2 pi by omega 0 multiplied by t d is 2 pi by omega d. So, omega 0 is the natural frequency and t d is the time period with damping, omega d is the angular frequency with damping. So, remember that in general time period is 2 pi by omega. Therefore, we have used the fact that t 0 is 2 pi by omega 0 and t d is 2 pi by omega d. So, that is what I have done here. So, 2 pi and 2 pi will cancel, this will give me omega d by omega 0. Now, what we need to do is to simply substitute for omega d. If you remember again, omega d is the frequency of the damped oscillator and that would be equal to square root of gamma square by 4 m square plus k by m. Of course, this has to come with the minus sign. So, we just need to substitute these things, k by m minus gamma square by 4 m square divided by square root of k by m, because this quantity k by m is equal to omega 0 square. And from here on it is some simple manipulations is what we need to do. So, here if you take root k by m outside, you will get 1 minus gamma square by 4 k m. So, just take root k by m outside. So, the root k m in the numerator and root k m in the denominator would cancel and the rest could be this. And now, to get the desired form, just multiply and divide by m here. So, you will get gamma square m divided by 4 k m square. So, we need to eliminate gamma, m and k, and for that we have this relation which we already calculated. So, it says that gamma by 2 m is equal to 1 by n into t 0. Let me write it out here. Gamma by 2 m is equal to 1 by n times t 0. So, I will have 1 by gamma square by 4 m square into m by k. So, if you look at gamma square by 4 m square, it is simply the square of this relation. square of this quantity. Hence, I will have 1 minus gamma square by 4 m square will be 1 by n square into T 0 square multiplied by again m by k is related to omega 0, that is because omega 0 square is k by m. Therefore, m by k would be 1 by omega 0 square, and this quantity is equal to omega 0 is 2 pi by T 0. Therefore, this will be 4 pi square by T 0 square. So, I can now substitute this as T 0 square divided by 4 pi square. So, clearly T 0 square will cancel. So, I am going to get 1 minus 1 divided by 4 pi square n square. This is T 0 by T d, and this was the required expression, and this is the answer that needed to be shown. The fifth problem is really the simpler problem, in fact, the simplest problem. So, it tells us that an oscillating system has resonant frequency omega m, and if driving is present, the width of the resonant curve is omega m by 5, find the q value. So, roughly to sketch the information here, it says that if you have average p as a function of omega, and maybe here is your resonance curve, and this is omega m, which is the resonant frequency, and the width here, this width is equal to omega m by 5, and we need to find the q value. So, the q value is simply the width is the resonant frequency divided by the width of the resonance curve, which is this quantity. So, in this case we do not need to know individually what is the value of omega 1 and omega 2. Basically, I do not need to know what is this value omega 1 and the value omega 2, because I directly have the information of the width. So, q is equal to omega 0 divided by omega 2 minus omega 1, and omega 0 is given as omega m, which is the resonant frequency, divided by this quantity omega 2 minus omega m omega 1. This is called the width of the resonance curve. We know what it is, that is simply omega m divided by 5. So, that would be omega m divided by omega m. So, that is equal to 5. This will cancel. So, the value of q for this system is 5. This is the required answer.